So I'm going to be talking about U-substitution. The definition says let G be a function whose range is an interval I, and let F be a function that is continuous on I. If G is differentiable on its domain and capital F is an antiderivative of F on I, then the integral of f g of x g prime of x dx equals capital F g of x plus c. If u equals g of x, then du equals g prime of x dx. And if I substitute both of those into this, I get the integral fu du equals capital F u plus c. So that's basically the definition. So I'm going to do a problem to explain this better. I'm going to do a definite integral problem using U-sub, which is basically used when you don't know the antiderivative of the function like how to find it. So if I'm given the problem, I equals the integral from 1 to 9 of 6 over the square root of x, the square root of x plus 2 squared dx. So I'm going to want to pick my u, and that's usually going to be the ugliest part of the problem. Like it might be the variable under the radical, but since there's 2 in this case, it could be all the expression raised to exponent or power, stuff like that. So in this problem, I'm going to want it to be the square root of x plus 2. And then du would be the derivative of u. So because the derivative of a constant is 0, we can disregard the plus 2. But the derivative of the square root of x, which is basically If I rewrite it, it would be x to the 1/2. And if I take the derivative of that, I'm going to get, by utilizing the power rule, 1/2 x, and then 1/2 minus 1 is a negative 1/2 dx. And because there's a dx in the problem, I'm going to solve for dx. And I'm going to get 2 du x to the 1/2. Then basically I just substitute u and du into the problem. So I would get and again, I could rewrite the square root of x as x to the 1/2. So these cancel, and I'm left with 12 over u squared. And I can rewrite that as u to the negative 2. So it's 12u to the negative 2. For indefinite, you wouldn't have these limits here, but in this case, because this is a definite problem, I'm going to have to change my limits to match the problem. So I'm going to have to plug in 1 and 9 into u and solve for my new limits. So the square root of 1 plus 2 equals 3, because the square root of 1 is just 1. And the square root of 9 plus 2 equals 5, because the square root of 9 is just 3. So 3 to 5. So then I'm just going to want to do the first fundamental theorem of calculus. And in the first fundamental theorem of calculus, the first thing you need to do is take the antiderivative of your expression, or part of the equation. So it's like the opposite of the power rule. So you're going to want to add 1 and divide by the power exponent. So negative 2 plus 1 is u to the negative 1, 12, and then divided by -1. So that would just be like -12 to the -1. 3 to 5. So because I've run out of room, I'm gonna have to erase a bit to do the problem. But basically, you plug in 3 and you plug in 5. But you do B minus A. So capital F of B minus capital F of A. So I would plug 5 into the antiderivative, and then I would subtract that. After plugging 3 into the antiderivative. Like I would subtract this from this. So I'm gonna keep this part and then work from the top. Okay, so there would be -12, and then 5 to the -1 is 1/5 minus -12, and 3 to the -1 is 1/3. So that would just be plus. So -12 over 5 plus 12 over 3 is 4. And I would want them to have a common denominator in order to add fractions. So times 5 is 20. So that would give me 8/5, which is the answer to the problem. If I was doing the second fundamental theorem of calculus, I just plug in usually the upper limit in for x, and if I needed to, I would plug in both the upper limit and lower limit for x, but then I would subtract the lower limit from the upper limit like we did. But you're plugging in variables. Also, you can do the mean value theorem and the average value theorem. In this unit. So that's basically it.